Hello, everyone. Thanks for coming back to our weekly seminar. So today we have the pleasure to have Daniel Siegel. So let me just introduce him better. He did his PhD in the Max Planck Institute for Gravitational Physics in Potsdam, Germany, under the supervision of Bernard Schutz. Then he moved to Columbia University, New York, with the NASA Einstein, as a NASA Einstein Fellow. Then he held positions as associate faculty at Perimeter Institute for Theoretical Physics in Canada and assistant professor in the University of Guelph, also in Canada. And now he is chair of the Theoretical and Physics and head of Plasma and Astrophysics group in the University of Greifswald in Germany. So without further ado, so Daniel, the stage is all yours.
Thank you so much. Thanks, Edgar, and thanks everyone for coming, and thank you for the invitation. It's a great pleasure to be here, visiting first time. And it's also a great pleasure to be able to share with you some, what I think are some exciting recent developments at the interface of a few different fields. So there's basically numerical relativity and modeling of strongly gravitating systems, but I'll also be talking about nuclear astrophysics. So the big question of basically where the periodic table comes from. So how the universe actually populates the periodic table. And also observational astronomy in the sense of multi-messenger astronomy. So observations we can do with gravitational waves and electromagnetic counterparts. So as Edgar said, I just recently moved back here to Europe, and it's great to be back to Europe. So this is the new group I'm setting up in Germany right now, in the University of Greifswald, which is north of Berlin, just right by the Baltic Sea. And I'll be highlighting a few results of these group members over the course of the talk. So basically the program today is to talk a little bit about so-called R-process nucleosynthesis, or so the synthesis of heavy elements in the universe. That is basically the underlying theme. And I'll highlight this with discussing a few different, very different actually, astrophysical systems. But there's an underlying theme in the sense that there's underlying similar physics in how these engines in a sense operate. So I'll first give you sort of a brief background on nucleosynthesis of heavy elements, and I'll move on then to discuss some recent developments on modeling neutron star mergers, so which are of great interest these days because of gravitational wave detectors and the observations we can do with them. And then I'll move on to show you how similar physics as in neutron star mergers is actually realized in some other astrophysical systems, in this case in so-called collapsed stars, so rapidly rotating massive stars that we think are the central engines of so-called long gamma ray bursts. And in the very end, if I still have time, I'll show you sort of a variant of this idea in the context of the pan-stability supernova mass gap, so very massive black holes that have been recently observed by LIGO Virgo, and how some of these concepts somehow, how some of these physics may apply actually in that context. So let me start with basically this general graph of basically an inventory of the elements in the universe. In this case, this is basically from our own solar system, but basically by extrapolation, a inventory of the elements in the universe. You can see the abundances of all the elements that are in our periodic table. And so basically the synthesis of hydrogen and helium by Big Bang nucleosynthesis, when the universe was just seconds to minutes old, is fairly well understood. We also fairly well understand how then all of these alpha elements up to the iron peak are synthesized through stellar evolution and supernovae explosions. But basically what has been a puzzle for quite some time, and still is an open problem today, so has been an open problem at least for 70 years or so, is basically the origin of half of these elements heavier than iron that are shown here. So basically all these elements are shown here in purple colors, all these sort of four bottom rows of the periodic table. And so up until today, we still don't really fully understand where these elements come from. So it's a fairly fundamental question. Now, the basic nuclear physics, or the basic mechanisms by how these can be created in principle, have been already worked out 70 years ago, so in the 1950s. It has been realized that if you want to go beyond these iron peak elements, there's basically you need to involve different processes than just regular fusion as in stars. There's two reasons for that. One reason is that these are the stable isotopes, the most stable isotopes we have in nature. So the nuclear binding energy per nucleon peaks there. And so you exhaust basically nuclear binding energy, so fusion is not really favorable anymore. But the second reason also is that the Coulomb barrier of bringing in new charges onto existing nuclei becomes prohibitive in forming actually larger nuclei by fusion. So you have to invoke a different process, and this was realized 70 years ago. And this is neutron capture. So you capture basically uncharged particles onto some seed nuclei, so you circumvent the Coulomb barrier. And this has been basically realized based on data similar to these ones. So meteorite data from the 1950s that were showing these characteristic two peak patterns, these double peak patterns here. And so they concluded that the universe was basically operating in superposition of two limiting regimes of this neutron capture process. So there's one process that's called the so-called S process, or slow neutron capture, where neutrons are captured onto these seed particles on a time scale that is much, much longer than for beta decay, so for the resulting nucleus to beta decay. So that's a necessity because capturing neutrons eventually makes these nuclei unstable, and to create heavier elements, you have to go up in charge number. So one of these neutrons has to finally beta decay to get you higher in charge number, right? So if you slowly capture neutrons, these nuclei will basically always equilibrate in a sense. So you will always produce stable isotopes, and so in the chart of nuclides, you may remember from nuclear physics, you would always proceed along this path of black dots here, so the so-called center of the valley of beta stability. Now, arguably more interesting is the other regime, the so-called R process, where the time scale here is very short compared to beta decay. So you basically bombard these seed nuclei, so let's say iron peak elements, with a lot of free neutrons, and those resulting nuclei don't have time to decay, and so you basically drift off from this from the stable isotope line toward the neutron-rich side of the valley of beta stability, and you realize the path that's basically highlighted here. And so you proceed along a path of very unstable neutron-rich nuclei. And the interesting thing is that there are magic numbers. So these correspond to closed neutron shells of these nuclei, where the stability is relatively high. So there's a large chance of capturing, of having nuclei in that state. So these are basically waiting points of this process. And so this translates then in abundance peaks once the process freezes out and finishes. So if you proceed along this center valley of beta stability for the S process, you get abundance peaks at these closed neutron shells, as you can see here. So these are the rightmost peaks in this double peak structure. However, with the R process, these peaks are formed far away from stability. So when they beta decay and proceed in the diagonal to the upper left to finally form stable isotope eventually, these abundance peaks are shifted to the left, and so you get this characteristic double peak structure. And this was already basically realized back in the 1950s. So let me this is a lot of words. Just let me illustrate this with a movie, which is probably much more intuitive to grasp. So this is from a simulation, from a neutron star merger simulation, following basically the fluid element as it is ejected from the merger site and undergoes the R process. So you can see here now the neutrons are capturing onto the seed particles, and you proceed to very high mass numbers. Now we run out of free neutrons. Everything has to beta decay back to stable isotopes eventually. Once there's no free available neutrons anymore to capture onto, and this process takes, in the end, basically forming these unstable nuclei takes a matter of a second, but then finally beta decaying to stable isotopes takes days to months to years to decades to centuries, even almost up to a Hubble time in some cases. So in the end, you get this characteristic pre-peak abundance pattern, the so-called R process pattern, which is nicely shifted with respect to the S process. And basically, by all these beta decays, a lot of nuclear binding energy is released, and that has observable astrophysical consequences because that's powering what we call a kilonova. And I'm sure you guys have heard about that before. So this is where basically the energy comes from. Now, over the last 5 to 10 years, we have actually gained a lot of observational constraints on how and where this process can happen in the universe. So this basic nuclear physics can be realized in potentially different scenarios. And one sort of agnostic way to look at this is basically to look at the parameter space of any type of astrophysical event that can potentially produce something like that in terms of the ejected mass of these outcast material as a function of the event rate of that process. And so you can basically figure out how much R process, how much heavy material there is in the Milky Way, for example, in our own galaxy. And there's obviously a degeneracy of producing this with a lot of ejecta at a low rate, or producing it at with a low yield and at a high rate. And so this is reflected by this black line with some uncertainty, some gray uncertainty regime. This is basically showing how much there is in our Milky Way. So this is what we basically have to produce with any astrophysical process. And now we've gotten a lot of interesting observations over the last 5-6 years that constrain or that basically break this degeneracy that's shown here in this gray band. There were some spectacular observations of dwarf galaxies, of ultra-faint dwarf galaxies in the Milky Way, in which only a few stars, a handful of stars, are heavily enriched with these heavy elements, and others are not. And so this points toward a process that is very rare and but has a very high yield of material at a given time. The same conclusion, and so this is basically what I would label as sort of early galactic history. So this was on timescales of many giga years ago. Sort of in more recent galactic history, we can actually look at our own Earth, and there's interestingly, some of these heavy R process isotopes are being deposited constantly. They are constantly deposited in our oceans and eventually sink on the deep sea floor. And so you can look at probes from the deep sea floor. And what people have been observing is that looking for these R process isotopes, they find an abundance of those that is smaller by orders of magnitude compared to meteorite data from the early solar system. So from let's say 4.5 or 5 billion years ago. And this discrepancy again can only be explained basically by a process that's very rare and but has a high yield, so that at times you get sort of a high deposition. But those radioactive isotopes decay with 80 million years half-life. And so eventually you decay sort of to a lower level. And again, an enrichment period event happens, and so on and so forth. So basically saying that the large variance that's been observed can only be explained by a high yield and low rate event. And so this creates this degeneracy. And so somewhere we have to be in this yellow region. This is basically if you translate these deep sea floor measurements into this parameter space, it has to live somewhere in this yellow region. And if you do the same thing for these dwarf galaxy measurements, like reticulum 2 here, you get likelihood ellipses that also point in this upper left part of the parameter space. So basically, this is saying we're looking at some event that must be high yield and low rate, at least as sort of the dominant enrichment phenomenon in the local universe. Now, this is basically looking at an integrated way, of a sort of time integrated way of this process. But you can also look at this, and observers do this. You can also look at this in a sort of time dependent way. So as a function of galactic age or metallicity. So here we see very metal poor stars, very metal high. These are logarithmic quantities in case you've never come across those. The sun is right here. So this is our solar system here. It's all relative logarithmic units relative to the sun, which is 0, 0 here. This is the amount of R process elements indicated by europium. And so you can see here that there's, if you look at halo stars, so stars in the Milky Way halo, those have a very high europium, so R process enrichment at very early times. So at very low metallicity. So these stars have been probably polluted by just one single event. And those have actually much higher europium levels than the sun. And if you look at the stars in the galactic disk, so those are these dots here, and you can interestingly see a negative slope in this plot. Now, if you want to basically invoke neutron star mergers as the enrichment source of these elements, you'll find that there's some tension with these data. So if you fit something like a galactic chemical evolution model, this is a very simple one just to illustrate the main idea. You'll see that you don't really recover this trend, but instead you have something that grows sort of on a longer time scale and then eventually saturates at something that's more or less flat. And that's because neutron star mergers follow star formation with some delay, right? Because they have to first be formed and then they have to merge via gravitational waves, and that can last up to a Hubble time in some systems. So there's a large delay with respect to star formation. And at the same time, what's mostly contributing iron at these late times are supernovae 1.8. And they follow also star formation with a similar delay time distribution. And those two basically cancel, and this is why you get this flat trend. However, if you invoke something that doesn't follow star formation, just 1 second. If you invoke something that does not basically follows star formation without delay, you can basically deposit a lot of europium early on, and then let it dilute later on as the type 1a supernovae kick in, and you sort of more naturally recover this trend. So this is just to say that it is not obvious per se that neutron star mergers might be the only game in town. So there might be other sources potentially contributing. You had a question. Thank you.
So I don't understand what the axis actually means, FE/H.
Yeah, thank you. So these are units that are used by observers usually. So this is basically the so these are logarithmic units of abundances. So it's the logarithm of the abundance of iron over hydrogen relative to the solar value. So basically this is 1 decade, right? So there's a factor of 10 here relative to the sun. And as you can see, so some of these, very metal poor stars, they are enriched by, factor of 10 more europium than the sun. There's actually some outliers that go much further on.
One question.
Yeah.
The regular core collapse supernovae, they don't contribute.
Great question. Thank you. I completely missed that point. So I've actually highlighted this here. So if you were to invoke regular core collapse supernovae, which were basically the first idea that came up in the literature in the last century, the problem here is that they occur at a very high rate. So this high rate is simply inconsistent with these observational constraints that we have, that there must be something that's much rarer that's occurring at a much lower rate, but at a correspondingly much higher yield. So basically this rate argument kind of rules them out, at least as the main contributor. So it's not to say that some core collapse supernovae couldn't do it, but at least as sort of the main process, there's at least a few orders of magnitude in rates that create the tension here. But I'll come back to this, and I'll show you how a rare type of core collapse supernovae can potentially do this. Okay, so this is to set the scene. So let me start with neutron star mergers first, because this is what sort of many people are interested in these days and are invoking as the main process. And so over the last 5 to 10 years, we've learned a lot about neutron star mergers and how they can produce these heavy elements, so how they can actually eject material. And we've learned a lot about these properties. There's basically 3 different classes of such ejecta, and I'm sure you have heard about this in other seminars. So there's so-called dynamical ejecta, material that's expelled from the merger site by dynamical processes. So this is these are tidal forces acting on the neutron star surface, but also material dynamically ejected from the collision interface once the 2 neutron stars touch. So this is happening on millisecond timescales. Then after merger, if you have 2 neutron stars, there's usually a so-called hypermassive or supramassive neutron star that's gravitationally unstable. And for some while, we can drive a wind, either driven by neutrino absorption or by magnetic fields from that object. And that can actually also significantly unbind material. And later on, finally, some of this debris material circularizes in an accretion disk around the remnant, and that can be a neutron star initially, and then eventually it may collapse to a black hole. And so you're left with an accretion disk systems, and there's in fact very powerful accretion disk outflows that can also unbind a substantial amount of material, as I'll show you in a second. Neutron star black hole mergers obviously can also contribute, but now we at least have from LIGO some idea about rates. And so it does seem as if these neutron star black hole systems might be subdominant by far, actually, relative to neutron star mergers in terms of the ejecta masses. But there's still a fair amount of uncertainty in all of this. But this is basically to say that I will mostly focus on these neutron star systems in the following. Now, how can we tell? This is something that most of you are probably familiar with. This is this concept of kilonova that I already mentioned. So in this neutron-rich material, so basically this is a plasma of neutrons and protons and electrons and positrons. And basically upon decompression, these individual nucleons form first alpha particles and then start with the neutron capture process. This is happening on a time scale of 1 second after launch. And the final beta decays, so mostly beta decays, heat up the material at very late times. So once the material has expanded by orders of magnitude in distance, and eventually the material becomes transparent to photons. So photons are the diffusion time scale of photons in these ejecta becomes comparable to the expansion time scale, and this is the time at which photons are then free to leave and create basically a quasi-thermal emission, and this is what we call a kilonova. So that's really all it is. And this emission, this quasi-black body quasi-thermal emission, is somewhere between the UV, optical, and infrared, and precisely where it peaks, in which wavelength band, and at what time depends on a lot of microphysics, mostly on the composition of the material initially at the time of launch, but then also on neutrino interactions, because neutrinos through the charged parent interactions here can actually change the number of neutrons and protons in the system, and so they can change exactly how many neutrons you have available for these neutron captors, and thereby dominate exactly the abundance pattern that you will get at the end, because it turns out that a fraction of these very heavy outprocess nuclei have opacities orders of magnitude larger than lighter nuclei. So the opacity can change by orders of magnitude depending on the exact abundance pattern, and that really changes the color and the peak time scale of the transient. Now, so far we only have one really confirmed event that we're confident about and that we can compare to, the first neutron star merger observed in 2017. This again, a summary of the observational data of this kilonova emission, 650 individual flux measurements from different groups put together here and fitted with some kilonova models. So basically, I just wanted to point out that there's this early blue component peaking on a time scale of a day, and then there's a red component peaking in the infrared on a time scale of a week or so. And the really surprising thing about this was that in order to explain the data, you would need a lot of mass, a lot of outprocess mass to explain the strong emission. It became immediately clear that this red part was quite at odds with all the numerical relativity simulations of dynamical ejecta that have been run basically up to that point. The blue component was still debatable to some degree. In some extreme part of the parameter space, there was still some consistency. But it was immediately clear that this red one was really odd. And so basically we realized that these post-merger accretion disks that I just mentioned may be a really good explanation for this. I'll get into a little more details in just 2 minutes. The blue component, however, was also quite mysterious. And I think up to today, there's no really satisfying explanation for this yet. But I'll argue in a few slides, we have some very recent results where I think we find a pretty consistent description of what may have been going on there. However, there's also other interesting electromagnetic phenomena that we are after. They have not been observed yet, but we might observe them in the near future. And they have to do with the fact that as this very fast, so there's a very fast tail of material originating from this collision interface. And this gives rise to a power law distribution of mass as a function of velocity. And so you can have a tail of material that goes almost up to the speed of light. And although this is just a tiny amount of material, so something like 10 to the -6 solar masses in ejecta, they possess a lot of kinetic energy. And so once they run into the interstellar medium, they create a shock wave, and the shock wave accelerates electrons, and those radiate synchrotron emission. And this is something that is potentially observable. So we've done some ab initio modeling based on these simulations recently, trying to predict these signals. They would typically peak on a timescale of years after the event. So this is something that peaks very late. So for reasonable parameters of the ISM. And there have been also recent observations of a potential rebrightening, actually, of the afterglow of this GW17-0817 merger. There's still quite some debate as to whether or not this actually is a rebrightening and how large the significance is. But if it is actually true and if it's actually physical, this is to say that we have now sort of ab initio models from numerical relativity that actually are able to fit this pretty well. So it is conceivable that the signal may actually be true, at least based on theoretical grounds. And something like this would also help us to distinguish between different scenarios, so between two neutron stars or a neutron star and a black hole, simply because in the neutron star black hole scenario, these collision interface ejecta are not there. So this is some important discriminant, potentially important discriminant in the future to look out for. The other component that's associated with this very fast materials are free neutrons. So it happens actually that the outflow is so fast that the individual nucleons actually don't find each other. The expansion timescale is so fast that a lot of these free neutrons, actually end up as free neutrons without being captured. And so this leads to free neutron decay on a timescale of the free neutron decay timescale 10 minutes or so. Something we've also explored here in detail with nuclear reaction network calculations and some tracer particle methods dedicated to this high velocity tail. And here you can see we nicely find the heating component, this excess heating component of free neutrons above the typical R process heating, which is just a power law. And so this early excess of available energy produces another astrophysical transient. So this is UV emission that is potentially observable. So here we've also included for the first time relativistic observer effects that also show that it's actually much brighter than previously thought. And if you compare this now with the GW17-0817 17-0817 data, you can see that it peaks on timescales of sub-hours to hours timescale, so much earlier before the telescopes actually got onto the event. So we unfortunately missed it. But this is clearly something to look for in the future. Again, this would not be present in the neutron star black hole merger scenario. So again, an important discriminant if we find early UV emission. So this is something interesting to look for. So now, where does the main kilonova come from? The main optical, so UV optical to infrared emission. So these are some recent results that we have, and I think they fairly consistently show how such a blue kilonova, as observed in GW17-0817, could potentially rise. So in this post-merger phase, you have this remnant neutron star, this hypermassive or supermassive neutron star. And there's a lot of very complicated plasma phenomena going on, instabilities. Magnetic fields are amplified by the Kelvin-Helmholtz instability. So it's basically the shear layer when the two neutron stars touch. Then there's a very complicated post-merger. There's basically a double core structure that bounces and stirs turbulence in the system. That gives rise to some what we call here post-merger turbulence that further amplifies magnetic fields. This is the toroidal magnetic field strength here shown as a function of time after merger. And eventually, the fact that this object is not rigidly rotating, but differentially rotating, also leads to so-called magnetic winding. So magnetic fields are wound up and amplified that way. And we nicely find this here in the simulation as well. So this is basically the typical rotation profile of such a remnant. Slowly rotating core, and then some rotationally supported envelope that gradually transitions into an accretion disk, as you can see out here. And so the interesting thing is that these small-scale magnetic fields that are generated by the small-scale dynamos, basically by these plasma instabilities, are eventually wound up by magnetic winding into large-scale toroidal structures, as you can see here. So basically teasing order out of chaos, so sort of an inverse cascade. And these toroidal fields eventually become buoyant. They become so strong, magnetic tension basically pulls them toward the polar axes, and they start to break out of the star and form a magnetic power along the polar axis. This is also helped by neutrinos. There's also strong neutrino emission from the remnant that also pushes out material and magnetic fields, basically, that's frozen into the material in these polar directions. And so we get actually a fairly nice magnetic jet structure from this remnant after merger. There have been very recent work also by other groups that have been exactly looking into the same idea. So here, but here basically involving some strong magnetic fields and large-scale magnetic field post-merger, or here using subgrid model and an alpha dynamo model to quickly amplify the magnetic field and help it break out of the star. But here it's coming basically self-persistent from the merger simulation out of the pre-merger physics. So here you can see again the toroidal field along this jet axis and how it eventually becomes buoyant and breaks out of the star. This jet then travels through the previously ejected material. So through this cloud, it plows through at multi-relativistic speed of 60% the speed of light or so. It eventually breaks out and forms a jet, which we find has a sort of modest magnetization of sigma 5 to 10 or so, and this gives it an asymptotic Lorentz factor of 5 to 10. So it's borderline to what may become potentially a jet for a long gamma ray burst. But these are still fairly modest Lorentz factors. But the interesting thing is that for short, yeah. So basically, you would need at least Lorentz factor of 100 or several hundred to explain some of the short GMB observations that we have. So this is really a very modest Lorentz factor here. But upon collapse, for example, it might once this collapses into a black hole, it might the baryon loading might decrease a lot, and so the magnetization can increase, and so the Lorentz factor would also increase by a lot. The interesting thing is that these polar winds associated with the jet and the jet disk interface create another new transient that we find here, which is another precursor. So there's basically this bump here happening on an hour time scale. So this is basically kilonova emission, if you want, from the material that is in this interface between the disk and the jet. This is the neutron precursor I was talking about earlier. So peaking on sub-hour time scales. So this is basically a new thing on our time scales, and then only comes the bulk kilonova later on. And so we think that the bulk kilonova later on comes from actually the disk. So here you see basically two snapshots of the disk, one at early times. Here you have the neutron star at the center. And initially we find that non-axisymmetric instabilities in this remnant drive the spiral waves into the accretion disk, something that's been observed before in other simulations. So there's several papers on this. And they can inject quite a number of, quite an amount of material, something like 1% of the solar mass or so. But still fall somewhat short in trying to really get to the blue kilonova, at least a few percent of the solar mass. But what we see instead is once the magnetic fields, the strong magnetic field set in, and so here you can clearly see MHD turbulence setting in the accretion disk that starts to destroy these spiral modes and adds angular momentum transport here, and that increases also the wind from the accretion disk and makes it actually much larger. So it viscously spreads in a very short time scale. And this is what you can see here. So within 10 milliseconds here, you basically double the amount of ejecta from the system. So we're basically arguing that perhaps within 50 milliseconds past merger, you would have enough ejecta to get to this, 2 or 3% of the solar mass limit that's apparently required.
Sorry, what is the green
Yes.
ejector?
So the green one, okay, good question, thank you. I skipped that. So the green one, and you also can see the legend here. So the green one are these polar outflows. So this is basically, if you just look at the in this polar region, the material that comes out here, that's fairly fast, but the baryon loading here is very low. So the total amount of material actually is fairly low. But if you look in this region here, that's everything that is basically coming from the disk. That's by far, according to our calculations here, is by far sort of dominating the ejector in total. But as I said, the screen part has this interesting observational consequence that you see this precursor signal. And here you can also nicely see how this increase in ejecta from the system is nicely correlated with the onset of a dynamo in the accretion disk. So here at the beginning, you see fairly chaotic patterns. This is again the toroidal magnetic field in the accretion disk. This is the disk midplane as a function of height above and below the midplane, and as a function of time. And you can see how nicely over the course of after 35 milliseconds, the first dynamo cycle set in. You see these alternating patterns of magnetic polarity, of magnetic energy created in the midplane, and then drifting off to higher latitudes where it's being dissipated and helps to drive winds. Now, if you do a detailed nucleosynthesis analysis, you find that this is all so-called blue material. So these are light R-process elements with a fairly low opacity. So they have nice properties to explain UV and blue optical emission. So if we run a kilonova model on this and compare to, for example, the GW170870 kilonova here, just to give a sort of reference to this, it actually fairly nicely fits those data points. And I just want you to focus here on the first couple of days, because then later on the red emission comes that's not included. But it shows nicely that the first few days of the blue kilonova can be nicely sort of captured with this mechanism. So moving on to the red part, how do we go beyond the first few days out into the weak time scales? And this is something that I already alluded to. Eventually, this remnant here will collapse to a black hole, and then you'll have accretion disk winds from the black hole disk system, which is something that we studied over the last 5 to 6 years in great detail. Here, the situation is slightly different, because you don't have a neutron star at the center that irradiates all the outflows with a lot of neutrinos, changing the composition of the material. But here you just have a black hole that's absorbing material, and there's no strong neutrino radiation from a central component. So what happens here is, and I won't go into the details here, but if you're interested, I'm happy to talk about it afterwards or so. There's an interesting self-regulation mechanism that we identified in these disks that basically drives it to a fairly neutron-rich state over long timescales. And so you can actually launch very, very neutron-rich material from the disk, which we find is in good agreement basically with the properties of what you would need to explain this red emission on longer timescales. Again, here there's nice dynamo structures you can study. There's a very recent, very long simulation by Yuji et al. That also now find these dynamo structures actually now over a much longer time scale. So they were able to simulate over a second post merger, which is quite an achievement in terms of the computational cost and everything that's involved. We were only able to study this for a few hundred milliseconds or so. We scanned the parameter space, and here now you can see the abundance pattern of the R process from low ejecta now actually extend all the way from the first to the third peak. So we can basically form all R process elements. The details obviously vary depending on the system parameters and so on. But the qualitative picture is that these post-merger disks around black holes in principle can synthesize a large amount of sort of a large region of abundances of the R process. And so there's lots of work on this over the last 5 to 6 years by many people, not just us. However, I should note also that, and I'll skip this in the interest of time actually, but I'll just make a quick note here that there's still some fundamental physics that we obviously don't understand here, and there's still substantial uncertainties with all this. One effect that has been only recently sort of appreciated and pointed out, and now there's a lot of work on this, is the fact that there's also neutrino oscillations involved here. There's a fast type of neutrino convergence that actually here in this calculation we showed for the first time plays an important role, or potentially an important role in post-merger physics, because the conversion of neutrino flavor changes the weak interactions and changes the composition of the material. And we basically demonstrated here that whether or not you include this effect actually makes a big difference in terms of, or can make an appreciable difference in terms of the composition of the material. And this translates into these R-process abundances. If you take into account neutrino oscillations, that can actually boost the opacity, will boost the opacity, but also boost the amount of heavy R-process material you can get from an event. So this is still a fairly much an open question, because also on a fundamental level, these oscillations are not really well understood yet, and so there's some assumptions that go into this. Now, looking ahead into the future, I recently speculated a little bit about, so if you sum up all of this, what might be actually the general engine in the universe to produce R-process elements. And so we can actually speculate a little bit about this, because we can assume some expected distribution of binary neutron star mergers as a function of binary total mass. So, for example, the galactic distribution of double neutron star systems, or something that's more akin to what LIGO is inferring these days for the system parameters. And we can convolute this with some predictions from numerical relativity simulations in terms of ejecta masses and things like that. And so if you do this, and so this is the exercise here I did, it's basically you can plot the ejected mass of the system as a function of its binary total mass. You have to assume an equation of state, and so there's some dependence here, but basically the quantitative picture is this: the gray band is GW17/17 with a total mass here of 2.7 solar masses roughly or so, and you can then also categorize it by the different ejecta channels, so disk ejecta or dynamical ejecta, wind ejecta, and things like that. And admittedly, making some crude assumptions, you can study the population to some degree. And so this led me basically to speculate that, in fact, GW17/17 might not be, a weird case, but rather it might be actually a fairly general case in terms of expected neutron star merger events, and in the sense that the total amount of ejecta should be dominated potentially by these disk ejecta, so that potentially the universe chose these accretion disks to synthesize most of the R-process elements. And even if we don't believe in neutron star mergers, I will show you now in the last 5 minutes or so how other systems can contribute to R-process in a very similar way, where again accretion disks play a central role. So this conjecture is basically also sourced by these ideas. And so I think this is fairly speculative. I might be completely wrong about this, and I'm happy to, but I think it's at least interesting as a conjecture to either falsify or find more evidence for in the next couple of years as we get more observations in. And at least with a few more observations of neutron star mergers, we will get a lot more information on this, and things will start to sharpen. Okay, so this brings me to talk about collapsars in the last five minutes or so. So these are, as I mentioned, basically rapidly rotating massive stars with a 0 main sequence mass of at least 20-25 solar masses or so. And we're looking at these subsystems, a tiny subclass that is also rapidly rotating at the time of collapse. These are basically thought to be the general paradigm for long gamma ray bursts. Because essentially what happens is that the star directly collapses, or more or less directly collapses, into a black hole. There's no proto-neutron star phase as in ordinary core collapse supernovae. or if so, only very, very brief, but no successful explosion, or at least in most cases, no successful explosion. But rather, you form a black hole, and because of the angular momentum in the system, material cannot just radially collapse onto the black hole, but instead is forced to accrete through an accretion disk, right? And so this accretion disk is what's thought to power a jet, and this jet is thought to power, thank you, a long gamma ray burst. Now we basically realized that the very same physics as in these post-merger neutron star systems might actually be operating in the early stages of such a collapsar. Basically what I'm showing here is the accretion history of such a collapsar. So basically taking a stellar model and letting it collapse into a black hole. And so you can basically measure what the accretion rate should be. And this basically defines the state of the accretion disk. And what we find is that in the very early phase, which coincides basically with the phase where you can power a relativistic jet to form a long gamma ray burst. In this very early phase, the accretion disk is very dense, and so the system resides at very high accretion rates. And so if you simulate those in sort of more detail, taking into account the relevant physics, we find that the density of the material, of the accretion stream is so dense that electrons become degenerate. And if electrons are degenerate, then it actually becomes very hard to produce electrons and positron pairs. So what happens is that basically electron capture on protons. So I should say that all of the accretion flow is so dense that anyways, all nuclear material is completely dissociated. So we're talking about individual nucleons. And under these conditions, electron capture on protons is preferred over positron capture on neutrons. And so what happens is that effectively the flow neutralizes. So you create an excess of neutrons. In other words, this sort of electron fraction parameter becomes very, very small. And you can nicely see this here. There's a very small electron fraction and a moderate electron degeneracy that's nicely coincides. And in these early times, if you look at the outflows, you can again nicely reproduce the solar abundances in our process material. While at later times, once the outer shells of the stars start to accrete, the accretion disk is much less dense, and the accretion rate drops, and then below a certain threshold, the flow does not neutralize anymore. And as you can see here with the green line, you only form light arc process elements, or no arc process element in fact anymore. So this is just iron peak here. And we find that if you take into account the rate of these events, as estimated from long gamma ray bursts, together with the yield that can potentially be unbound from such accretion disks, we find that such collapsar systems could actually be a sort of really significant contributor to the galactic arc process. So you can unbind something like up to tens of % of a solar mass in one single event, potentially. And the rate is, the long gamma ray burst rate is somewhat lower than the binary neutron star rate, but the higher yield basically overcompensates for that fact. So it can be actually a significant contributor. So the question is, right, this is an interesting theory, or might be interesting theory, but how can you actually tell, right? So how can you actually observationally tell that something like this is going on in the universe? And so the idea here is that in some cases, you co-produce a lot of nickel 56, either through a very brief proto-neutron star phase, so like in an ordinary core collapse supernova, or because of part of the disk winds. And so basically what you have is a transient, or it's a transient that looks basically like a type 1c, like a broad line, so-called broad line type 1c supernovae that's thought to accompany many GRBs. But then inside, in the skies, there's some R process. So there's basically a kilonova, or it's like a strong version of a kilonova within this supernova in the skies, and will only show up at very late times once the supernova once the supernova is fading. At very late times, the R process, because it's a power law heating, will eventually dominate over the supernova heating, and you will get some sort of kilonova emission at very late times, and you can try to predict some light curves in spectra. Typically, the process the timescales at which to look at this is hundreds of days after the main peak. So this is at really late times, which is also challenging to observe, but maybe not impossible going into the future. Now, if I still have 2 minutes left or so, perfect. I just want to give you another spin of this idea, because as you may know, the gravitational wave detectors are finding interesting objects. So they're finding primary black holes in binary black hole systems that actually reside in this so-called pan-stability supernova mass gap, which is between roughly 50 and 120 or 130 solar masses, depending on models. Where actually, according to conventional stellar evolution theory, no black holes should reside, because what happens in the core collapse of these systems is that basically the so-called pan-stability sets in, and that leads to explosive oxygen burning that completely disrupts the star and doesn't leave any remnant behind. So there should not be any black holes formed in conventional stellar evolution. Nevertheless, we do see them in some of these systems. Apparently, there's at least good evidence for them. So the question is, how do we explain these systems? And there have been several ideas in the literature that I don't want to review here, but I just want to give you another idea, which is this one, which is a fairly conventional idea, and it's exactly this collapsar idea that I described earlier. So we're contemplating here the possibility that very massive objects above the pan-stability supernova mass gap might actually be collapsars, right? So let's sort of assume that maybe there's a tiny fraction of those systems that are rapidly rotating, and if they are rapidly rotating, they would form, what we call these, so super collapsars, so very, very massive collapsar systems that again lead to a black hole with an accretion flow around them, and due to the mass loss through disk winds, they will actually populate, and they will actually, fall into this gap and populate the pan-stability supernova mass gap from above, so to say. And we find that, taking some of the, stellar models by Renzo et al., we can actually, depending on model parameters, so basically on what you assume in terms of rotation of these stars, you can populate basically the whole range of black holes here. And interestingly enough, also these stellar models here, for example, those by Renzo et al. Are really compact stars, so that again the accretion flow at early times is very high, and we were really surprised to see that, and happy to see that the accretion rates initially are again at a very high, in a very high regime, where again electron degeneracy will drive the accretion flow neutron rich, and you can potentially form outcroppings. And these are really massive systems. So the interesting result here is that basically you could, in principle, it is conceivable that you could, in principle, produce up to even a few solar masses of outcroppings in one single event. However, those would be very rare, right? So we're not in any sense claiming that they are significantly contributing to the galactic outcroppings, but this is at least it is at least an interesting possibility. And this would also be observable. So in this case, we're definitely not looking at an accompanying supernova, because those systems are so massive, there's basically no chance to have a successful supernova explosion prior to the black hole formation. So here we would really just see the outprocess material in a very transparent way in some sense. So there's no other accompanying transient. We also find there's actually a lot of nickel-56 co-produced, but only at late times. And so it's a combination of a nickel-56 driven transient like in supernovae, but also with outprocess elements. And so these outprocess elements make the spectra and light curves very red. So we find that basically these are infrared transients, and they show very broad lines because again these disk winds are roughly 10% the speed of light, so fairly fast. So you see fairly broad lines in the spectra, and so it would be fairly easily able to tell them apart from other transients that might be there in the infrared. And so we did some sort of order of magnitude estimate here to show that basically with upcoming surveys like the Roman Space Telescope, for example, one could be in principle be able to pick up at least a handful of these over something like 5 or 6 years of the survey period, if these things are there. But there's obviously a lot of uncertainties in estimating the rates and so on and so forth. Okay, and this brings me to the conclusions. So I was trying to motivate that neutron star mergers give rise to various kinds of ejecta, and we're still studying them in great detail. And there's a lot of research that still needs to go into this. But there's a broad range of these components, all with different properties. We have the first basically self-consistent ab initio modeling underway of multiple electromagnetic counterparts, all basically consistently from one simulation. So not non-thermal emission, but also thermal emission. So there's a lot of things being done in the field. We find now for the first time also interesting astrophysical jets, so bipolar jet structures from hypermassive neutron stars that have interesting observational consequences. We find disk outflows consistent with something that's similar to GW170817. And basically, still the black hole disks at late times then take care of the red kilonova. I was telling you about this conjecture that summing up all of this, potentially accretion disks are really the path that the universe chose for our process. Nucleosynthesis here is just a bold claim at this point, but maybe something interesting to really look for in the next couple of years. And that's, as I said, also sourced by these other systems, the collapsars or potentially even super collapsar systems. And I'll stop here really and thank you for attention, and I'm very happy to take any questions.
Well, thank you, Daniel, for such a nice talk. So we have time for a few questions. So anybody has questions?
Yeah, the collapsar model, could you also have this accretion disk from a binary system, or that's not possible?
Yes. So you mean from a neutron star binary or from a stellar binary?
Yeah, instead of having very massive star, because there's some evidence for the type 1 BCs and so type 1 Cs that they might come from binary.
Yeah, that's
very massive stars, lower mass stars.
Yes.
Could you form such?
In principle, yes, I guess. There's a curious question. I've not given that possibility a lot of thought, but in principle, I think it's conceivable. I mean, it will very much depend in the end on how dense these accretion disks will be. I mean, for sure, due to the angular momentum in the system, you will end up with some sort of accretion disk one way or the other. But the problem will, so the question will be like how dense, how much material do you have in the accretion disk, and how dense will it be? So what will be the accretion rate? Because basically what we find here is to a zero order, what defines all the nuclear physics in these systems and decides whether you get heavy elements or not is really the accretion rate. So if the accretion rate is high enough, say on the order of a few percent to tens of percent of the solar mass per second, which is very high. So these are extremely hyper-accreting disks. Then you could get into this regime. But it will really depend on what the expected accretion rates are. And that I don't know off the top of my head, but maybe you have some numbers in mind. Yeah. Yeah, it's a curious question.
Is there any other question for Daniel?
The spin of the components for this binary, the neutron star binary plays some role in the modeling?
Yeah, that's a great question. So yeah, the answer is yes. I mean, so the spin does determine the amount of ejecta you can get. So for the post-merger accretion disks, so the post-merger accretion disks are a very robust feature of neutron star mergers. So because there's always some angular momentum transport processes that will expel some debris in an accretion disk. So no matter basically what the relative spins are of the neutron stars, maybe except for very, very extreme cases, you would still get an accretion disk. And in fact, in some combinations, you can show that you even get more mass than in other combinations or without spin. So for neutron star black hole systems, obviously it's very decisive. So there you need a high spin of the black hole for any accretion disk to remain. Otherwise, the star just plunges into the black hole, right? So this is what makes me a bit pessimistic about the neutron star black hole systems. In fact, because we've now seen or potentially seen 2 events with LIGO where basically this mass ratio is 5 or 4 to 1, meaning that maybe all the Unity systems are rare. So equal mass systems are rare, and then if you have a mass ratio of 1 to 4, 1 to 5, and upward, you would need a lot of spin of the black hole to actually realize some accretion disk, and so that would be interesting to see in the future. So there it can be very
So for the binary neutron star, so you would expect that the initial shock of collision will be significantly different or like different spins, but then later it's kind of
exactly. So it will heavily influence the merger, the direct merger phase. But then if you just look at the amount of material you get, the amount of sort of bound debris material that will circularize and form an accretion disk, that is a fairly robust feature. And obviously the actual numbers change depending on the spin to some degree. And as I said, in some cases you can show that there might be more mass than in others. But it doesn't change qualitatively the presence of the disk. What's very decisive is the total mass of the system. So if you have 2 neutron stars that are very massive, there's a so-called threshold where we call it a prompt collapse. So where basically directly within the first few milliseconds of merger, the whole system collapses into a black hole. And in these cases, there's not much time to shed mass and to have angular momentum processes at work that would move material out to some orbits. And so in those cases, you basically end up with very, very little material as an accretion disk. So that is really a very sharp transition and can be very decisive in that. But sort of the current equation of state constraints with this maximum mass with which this threshold scales seems to be such that at least for the ballpark of DNS systems, of double neutron star systems, those would not promptly collapse. So you would have at least some delayed collapse, and therefore, accretion disks forming.
All right, we have time for one last question. Okay.
So, because before the kilometers as the release of virgin neutron stars, the most energy injected phenomena in the universe were supernovae. And as far as I remember, so some decades ago, the models predicted more or less the abundance of the elements in the universe. For instance, gold will come out from supernova explosion and so on. But at least that was the idea that someone on the field, not on the field that I wasn't, but that read books, papers for the public, and that went to seminars like that. That was the impression that I had.
Yeah.
And suddenly, kilonovas appeared, and the picture changed. Now we really know, and I have a model of explaining the elements. So my question is a kind of sociological question.
Right.
Is it true that the problem was known some decades ago and hidden? Or is it that people that work in the field hope that indeed the supernovas would somehow explain the heavier elements, but the really heavy elements were not there, but maybe could be, and so that kind of stuff.
Yeah.
So, since you are in the field, maybe you don't have the impression that I have.
Yeah.
But since you are really in the field, you read those papers. So maybe you can answer.
Yeah. Thank you for the question. It's a great one. I mean, I wasn't around at that time when 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 those things happen. So I can only give you my recollection of as you say, reading some of those papers and going through some of those calculations. And so I would say it's a mixture of some of the things that you mentioned. So it was really thought that the supernovae could produce heavy elements, and also in the amount that we need to explain the galactic arc process. But there were a few things that were not known, like in the 80s and 90s, when some of these models were published. And so there's one problem that the supernova mechanism itself was not well understood yet, or at least it was thought the typical bounce mechanism was at some point realized to not lead to a successful explosion. Then one introduced neutrinos, and then it was hoped that the neutrino delayed explosion would eventually do it. And so there was on the one hand side, I think, a problem in understanding what's actually going on in the explosion itself. And then there was the separate problem of trying to do the nucleosynthesis calculation and trying to predict abundance patterns. So as far as I remember, it was concluded in these models that would explode early on that you could in principle form arc process elements. That is somehow conceivable because if you start with very neutron-rich material from the neutron star surface and you eject it fast enough, and you don't expose it too much to neutrinos, they will produce arc process and it will be fairly robust. But I think over the time it has been then realized that it's actually much harder to explode these stars, and you need a lot of neutrinos to make them explode. And so if you expose the material long enough to that neutrino emission, that raises the electron fraction, so it converts neutrons into protons, and then the so-called electron fraction becomes very large, and then eventually you would not produce heavy arc process elements anymore. So so one aspect is that now we think these systems are all undergo very delayed explosions. If they actually successfully explode, for many systems and many simulations they don't. But if they explode, they need a lot of time. And during that time, basically, it's impossible to undergo an arc process because all the neutrons in the outflow will be converted. A lot of those neutrons will be converted to protons, and so you have roughly equal numbers of neutrons and protons. So then the other idea was then that maybe in this post-explosion phase, when you have a protoneutron star, a hot protoneutron star sitting there and then cooling through neutrino emission, that this protoneutron star will drive a wind, neutrino-driven wind, and for some time, the models seem to indicate that these neutrino-driven winds could have an electron fraction slightly below 0.5, so with a slight neutron excess. So the problem is, right, that to unbind these nucleons from the stellar surface, on average, they need to absorb roughly 10 neutrinos, and so they change. So neutrons change into protons 10 times. So you basically erase the original composition, leading to roughly equal numbers of neutrons and protons on average. But it was thought that you could still create a slight neutron excess, and so produce at least some light arc process elements. But then, after 2010, a few things happened. So on the one hand, people looking at neutrino radiation transport and all these nuclear processes figured out different cross sections and things like that, and so that changed the calculation to become slightly proton-rich, actually. So that basically made it completely detrimental to obtain arc process in these winds. And then also the second idea that was not known until basically the 2010 years was what I showed at the very beginning, these constraints here. So basically in this parameter space, there were no constraints on where the events could lie. And so having a quark-galaxy supernovae up here with a high rate was perfectly fine. But then what was realized in 2010, and that was coincidentally, interestingly, around the same time where this theoretical concept of kilonovae came up, we actually got constraints here on that sort of break this degeneracy. So we had observational, so then there was observational evidence that that core collapse, ordinary core collapse supernovae at least would not do it as the main process. And then and then coincidentally, at the same time, also a few of us realized that the nuclear conditions would actually change. So yeah, it's a very long story, and I don't know all the details, but this is sort of my vague recollection. Yeah.
So, yeah. Okay. One very quick question.
Do your presentation what is very important is the way you describe the S and astrophysics. And as far as years ago, they are still unknown. The field of astrophysics is not theoretical, not really imagine a lot compared to the gas. The question is all these kind of effects are predicted in the
Yeah, thank you. That's another great question. So so I have to admit here, I totally agree with you that so basically these are all the nuclei, right, we know of, right? At least theoretically. And from the nuclear physics part, the only well-measured nuclei are really the stable nuclei, right? And so then going slightly off these heavy isotopes actually becomes very complicated in lab because they only live for a short time, and so you need to be, experimentally very clever of how to measure them. But this is now actually being done. So the point is really that these calculations, like the one I showed you here, really is based on theoretical models. So we for most of this parameter space, we really don't know the parameters. But this is now being done. So there's two big facilities that are looking at this. So there's FRIP at Michigan State in the United States that's actually has just started. And is now taking data, and so they're really trying to map. So it's really pretty impressive. It's a pity I don't have a plot here, but it's pretty impressive of what they project to be able to do in the next couple of years. So they want to map this whole space here in terms of masses of the nuclei, the beta decay rates, and so on and so forth. And then also here, and then also in Europe, in Germany, the GSI in Darmstadt fair, which will also go online hopefully in a few years from now, has the same target. So we'll get a lot of experimental data on this in the future. Thanks.
So I think we should thank the speaker now.
If you enjoyed the video, like and subscribe.